We have the lecture on the topic power system stability, and is for undergraduate BTech program of second year in electrical engineering. This part of the lecture, which is being recorded, is for the day one, and I recorded at the last. I have already recorded 4 lectures on the topic process stability, referred as day 1, day 2, day 3, day 4. And then this will be for the day 1, and then we have it day 2, day 3, day 4, and day 5, right? So there will be 5 recorded lectures on the topic process stability. What are the objectives of this lecture topic? We want to know what is the process stability. In fact, how we define the process stability. That is the first learning objective. Second one is the power angle characteristic, and how we draw the what is the relationship, how we obtain the power angle characteristic. So, and this power angle characteristic lecture, it is recorded in the from the day 2 onwards. Then this will follow next learning goal, that is the how do we analyze the transition stability using the equilibrium criteria, and this is recorded in the video lecture of day 4, day 3, and day 4. Then again, going further, the last learning goal of the chapter is how we can determine the stability using the criteria. It is for the different cases, or you can say the different applications, and this has been discussed in the recorded lecture of day 5. This course lecture is being delivered by Nankishore, working at IIT Allahabad. And in fact, I have this slide mainly to give due acknowledgement to the different authors who have their books published. So here I have listed some of the books which I have referred in the preparation of these recorded lectures. And then again, another one also includes some lecture slides from Prabha Kundur. Then also, because some of the figures I have referred from internet, and thus I have due acknowledgement to the PPTs or the image files which I have used in my lecture slide from unknown authors. So due acknowledgement to them as well. So this is the slide to know what is the process of stability and then how important it is here. Now, first one, we must know that we have the generators. In fact, we have the generators and we have several generators in the network. And thus, we have generators in the power plant being interconnected to another power plant, and then again you may have a load in the system. So you have actually a wide area network having several generators, not only in one power plant but in several power plants. And then you have the load widespread, and you also have a network widespread. And as such, it is very important that these generators which are in operation, they are operating in synchronism form. So what we refer here, the word synchronism, is that they are in synchronism with respect to other generators. So that means all the generators, they are in synchronism, they are operating at in the same frequency deviation, or and then have the same voltage deviation. In fact, it is desired that the generators, they have to be in synchronism within the tolerance or acceptable limits of frequency deviation and voltage deviation. We will discuss about these two quantity, deviation quantity, later in slides. Now, if in case these generators they fail to operate in synchronism, then what could be the consequence? In fact, as a result, if they are not in synchronism, there would be a relative motion which will change to take place. And if it is too much, so that means if there is a high relative motion that is taking place between the generators which are in operation, as a result, it will result, you will have the oscillation which are uncontrollable, and this will be in the grid, and that may result into the damage of generator. So if I consider you have, let's say, the oscillation of shaft of the turbine, see steam turbine generator, right? And if you have the torsional operation of the steam turbine generator as a set, then in that case it may result to its damage. And then again, that is one example here. So it is important that these generators, they have to be in synchronism. Normally, if you want to have the synchronism operation, there has to be acceptable range of frequency deviation, because we can say that frequency is very much related to the active power. And if there is a mismatch between the active power generation and the demand on the load side, it will result into frequency deviation. And thus, if we want to maintain the synchronism operation of the generators and we do not allow the frequency deviation to deviate beyond the acceptable limits, then in that case, we have the use of relays. We have over frequency relay and we have under frequency relays. So these relays will detect the undue deviation in the frequency, and then it may trip the generators uh, before its damage takes place. Yeah. And thus we are able to maintain the synchronism operation. So that means if the relay strips the generator, that means the generator is out of the network. Yeah. Now this stripping of generators, that means the outage of generators, it will prevent the damage. And let's say that in that case, it is power, because if you have, let's say, total generation and total demand, and thus, let's say that system is at steady state. We will discuss about the steady state condition later on. So let's say that we have a perfect match between the generation and the demand, and suddenly you have, let's say, increase in the load demand, and your generators were operating at rated capacity. So if I say that you have 5 generators and each generator they are of 500 megawatts, so as such total generation capacity is something 2500 megawatt. Now, all these 5 generators, they are operating at the rated value, and thus you have maximum generation capability available now, and they are in generation condition. So in this case, let us say that you have the increase in the load demand by further 200 megawatt. Then 200 megawatt increased load cannot be met from the generation which is available, and this will result into under frequency, and thus the frequency will drop from 50 hertz. And then if the frequency drop is beyond the acceptable limit, then these relays and the frequency relay will trip one of the generator here, right? And then again, during the, if one generator goes outage, then at the moment now you have only 4 generators here. Load remains connected. Load is of 2500 megawatt, but one generator goes outage. So now the total generation which is remaining, it is 2000 megawatt only, and thus again the further deviation in the frequency will, that means the frequency will drop further, and this will result into a worst case here. Right. If it, that means we do not have the load interruption. Right. So in this case, it will lead to have further deviation in the frequency, and then it is possible that another generator, the next generator goes outage, and then it will result into one by one outage of generators and resulting into the blackout occurrence here. So that means complete power supply cut here. Now here we have in this slide some of the terms, some of the in fact terms, common terms that we normally use when we have when need to have the understanding of the power system stability. The first one is the operating quantities. These operating quantities refers to either the electrical quantities or the physical quantities. That means electrical or physical variables, right? And this describes the operating conditions of the power system. So that means you have electrical quantities. It could be, let's say, the real power, reactive power, apparent power, voltage, or the current. So these quantitative variables, they define the operating condition. Then along with this, we also have, let's say, physical variables, rotor angle or the frequency, speed, in fact, speed of the generator. Those are the physical quantities. So they also describe what will be the operating condition of our system. Yeah. Then next common terms that is important, it is the steady state operating condition. Yeah. So in fact, it is the operating condition for which uh, all these operating variables, that means the power, both the real power, apparent power, and the voltage and current, frequency, or the speed, all these operating variables which characterize the system, which characterize the power system, they remain constant here. So that means if I say that you have a perfect match of power generation and the demand. So that means because normally you have load changes. So if you are able to have a match of the generation against the variation of the load demand, and thereby restore these operating conditions, operating variables, right? If you are able to restore the operating variables to the nominal value such that they remain constant, then in that case it is referred as steady state operating condition. Now the third one is the synchronous operation of generator. As continuing to the previous synchronism word that we referred in the previous slide. In fact, a generator is in synchronous operation because a generator is normally connected to the network, yeah, or it may be several generators in the system. Yeah. So we want to have the synchronous operation of one generator along with respect to the other generators in the system, or it may be, in fact, what is deferred here, other generators. So it could be the synchronizing operation of one generator with respect to the remaining generators in the power plant. And then again, when the same power plant is connected to the network, then we can say that one generator, synchronizing operation of one generator or several sets of the generator or the power plant is with respect to the network. So this is how we can say the synchronism operation of a generator. And what it refers here, it says that according to this synchronism operation, it says that average speed and thus the frequency of machine of the generator, if it equals to the angular frequency of the AC network or the electrical speed of other machines here, then you see that it is the synchronism operation of generator. So that means electrical speed of one generator with respect to the electrical speed of other generator in the power plant, or you can say the frequency of the signal of the generator with respect to the frequency of the signal in the network. So that should be the same here, or equal, you can say. Then I refer some of the definitions when we have to study the power system stability. And the first one, what is power system stability? How we define it here? In fact, it is the ability of electrical power system, which is at one operating point. So, which is at one initial operating point, and this could be at steady state condition, as referred to the previous slide. So that means steady state condition is that operating point for which the operating variables remain constant here. So we consider that ability of electrical power system at a given initial operating condition to change to the new operating point with equilibrium. So that means you have an electrical power system which is at initial operating point at a steady state condition being changed to new operating point in equilibrium condition following the disturbance here. So that means if I say that you have perfect generation and demand match, and let's say that there was a change in the load, and you are also able to change the generation so as to match with the load. So now this is your change operating condition. So one operating condition was steady state, and if we are following the load disturbance, so change in the load condition, it is a disturbance here. And if your generation is able to match to the new load condition of demand, then it will be a and reaching to the equilibrium. Then in that case, it will be referred as power system stability. And we say that when the power system changes to the new equilibrium point following the disturbance, having the variables, that means all the quantities that characterize the system, right? So having all the system variables within the limits, within the acceptable limits, such that system integrity is preserved. It means that when we have the change in the operating condition, there was, let's say, the change in the load, or there could be also a line trip. So there, let's say there were two lines and one of the line gets stripped, but still in that case system integrity will not be preserved, right? So but if I say that there is a change in the load and generation is changed such that it matches with the load, so here we do not change, we do not cut the load, right? We are able to have a increase in the generation from the generator to match with the load demand. So we have not cut the load here. And as such, system integrity is being preserved here. Having the system variables within the limits with the system operating condition being changed to the new operating point here of equilibrium. Right? So that is the power system stability. Now this integrity, further I say illustrate, this integrity of the system is preserved when practically the entire power system remains intact, as I said, without any tripping of generators or the load. Yeah. So that means you do not allow, if you have some disturbance, you do not allow either a generator or the load to be outage, to be cut. So then only we say that system integrity is being preserved, it is being intact here. But if in case there is a generator cut or the load cut, or let's say the line, some disturbance takes place and the line is cut, one circuit is out, then in that case system does not remain intact here. Now this power system stability is another way we can define, and it is we say in terms of defining the condition of equilibrium between the forces. And here we see the condition of equilibrium between electromagnetic torque that is on the generator side and the mechanical torque that is from the turbine side. So that means if the two torque which are in opposition, if there is a condition of equilibrium being achieved, being attained between these two torque, then we say the stability is maintained here. We will discuss more in detail about these talks later on. Now, if in case system was at initial operating point and following the disturbance, and system will change to the new operating point, but equilibrium is not achieved, let's say, right? That means this condition of equilibrium is not achieved at new operating point. Then in that case, instability may result. And whenever disturbance leads to sustained imbalance between the forces here. So that means system operating condition is changed to the new value for which the condition of equilibrium between the forces are not achieved. Then this will result into sustained imbalance between the forces, and thus instability will take place. We will discuss this about this later on, what is instability. And this definition referred from this paper. And next, continuing with this, so ability of the power system to, that means say, to maintain synchronous operation following the disturbance here. Now here it is said transient disturbance, so that means more severe form of disturbance here. Right, so more severe form of disturbance could be, let's say, you have a fault on the line, you have a transformer or the buses, or maybe some outage of generation. Because when we have the loss of generation, that means one complete generator is out. So it could be, let's say, 200 megawatt generator or 400 megawatt generator is suddenly cut. So that is again a transient form of disturbance. Or there could be also a load. Though it is placed at the third number, because load suddenly do not cut unless and until the complete circuit, the complete network that connects a particular region being disconnected. So we normally don't have a large amount of load cut being suddenly. Then we have what are the factors that decides the stability. In fact, how it influences the stability. Uh, in fact, this stability being attained to the new operating point, it depends upon what was the initial operating point here. And then again, what was the magnitude of disturbance. For example, if I say that we have 5 generators and all these 5 generators, they were operating at rated capacity, and the total generation was 2500 megawatt. And you have a load of 2500 megawatt, and if there is a further increase in the load by, let's say, 200 megawatt, then total generation cannot be increased this one again. So now your initial operating point is 2500 generation and 2500 megawatt load. So this is perfect math, steady state condition. But if in case there is an increase in the load by further 200 megawatts, so increase in generation cannot be achieved now, because your generation is at maximum rated capacity here now, right? And here the load change is by 200 megawatts, right? So generation cannot be increased by 200 megawatts. But if I say that load condition increase is just by 5 megawatt only, so out of the 5 generators, and if I say that 2510 megawatt, so there is a possibility that you can overload your generator and thereby meet your demand increase of 10 megawatt. So that is possible. So that means here the initial condition of the system was 2500 megawatt, and increase in the load, if I say 10 megawatt, so this can be achieved. This can be stability can be maintained. That means the disturbance is just by 10 megawatt. So this can be maintained. Equilibrium can be achieved. But if the increase in the load by 200 megawatt, that cannot be achieved here again by varying the generation. So that's the what is the initial operating point and what is the magnitude of disturbance. But if I say that your total generation available is 2500 megawatt, but total generation at that instant was only 2000 megawatt. So that means you have still a margin of 500 megawatt. So that means if I say there is an increase in the load by 200 megawatt, right, then in that case your generation can be increased to match with the demand of 2200 megawatt. That is possible. So thus the stability being achieved following the disturbance will depend upon what was the initial operating point, and then again what is the magnitude of disturbance here. That is important. And again one should understand that the operating condition that remains after the disturbance, and it is very much different from the condition before the disturbance here, right? And then going further, what is disturbance in the power system? Let us understand. In fact, this disturbance in the power system can be a sudden change, or it could be a sequence of changes actually, and it will result into one or more parameters of the system here, or thereby one or more of the operating quantities here. So that means you may have a disturbance as a sudden or a sequence of one small amount change, then after a certain time, then again small amount change, and then after a certain time another amount of change. So but it will result into parameters. So that means the quantities, operating quantities to change here. But this change in the operating quantities will depend upon what is the magnitude of change here. And as such, we have two different types of disturbance. One is the small disturbance here. Now, In fact, what is small disturbance? It is a disturbance for which the governing equations that describes the power system behavior, power system characteristics that can be linearized here for the analysis purpose. So, for example, if we have, let's say that 2500 megawatt generation and 2500 megawatt load demand, and this is perfect match, and if in case I consider that there is an increase in the load by just by 10%, right? I'm sorry, by just by 10 megawatt, then in this, for this increase of 10 megawatt, the governing equations which describes the behavior of the system dynamics that can be linearized, because normally your generators, if I refer, they can be modeled as if I consider the swing equation, they can be as second order model. If I consider one, include one more quantity, terminal voltage, it could be as a third order model. And then again, if I consider field circuit part, and then again damper winding and so on. So we can have the modeling of the generator fifth, sixth order model. Now, these equations, governing equations for that describes the dynamics of the generator, they are non-linear. Non-linearity, I can say that, let's say, if you consider the of characteristics of a generator. So if I have on x-axis variation of the field current, and then on y-axis, if I have open circuit voltage of stator winding per phase quantity. So in that case, what is the variation? So for a certain range of variation of the field current, the variation in the open circuit voltage, that is linear. But further increase in the field current, you observe that there is a saturation in the characteristics here, and thus your generator normally it operates in a non-linear point here. And then again, you have several other machines, several other systems which has the non-linear characteristics here. So thus, for the case of small disturbance, and these governing equations that describes the behavior of the system, they can be linearized. Then in that case, it will be referred as a small disturbance here. But if in case the changes, the disturbance, each of such magnitude for which these governing equations, they cannot be linearized uh, for the analysis purpose, and then such kind of disturbance will be under the category of large disturbance. So if I say that, for example, sudden outage of a large generator in the system, or suddenly a large amount of load is cut out, or you can say there is a line trip. There were two circuits, two parallel circuits, and one line, one circuit is completely cut out. So that is again a form of a large disturbance. So that is how this is how we say that what is a small disturbance, and another one is a large disturbance here. Now let us understand what is steady state stability here. Now, in fact, as I said that as per the definition of the power system stability, it refers to the ability. So we use the same definition, similar definition, in fact. So ability of the power system to remain stable, because we say steady state. So ability of the power system to remain stable following a small disturbance. That means following a small amount of disturbance and then reaching to the steady state point. So that means your operating variables, voltage quantity or the frequency quantity, they are near about constant. This is how we have defined the steady state operating condition. So that means steady state stability refers the ability of the power system to get stable following a small disturbance, and then reaching to the new steady state operating point here, which is identical or very close to the pre-disturbance operating condition. And this is known as the small disturbance stability of a power system. Then again, since as we discussed in the previous slide, we have a large disturbance here. So thus, following from that, we have another form of stability, and that we call it as transient stability. Again, it is the ability of the system to maintain synchronism following a transient disturbance. So that means your power system ability to remain synchronism following a large disturbance of, let's say, a fault type or a large generator outage or a large amount of load outage here. So that is your transient stability. Now, system response for such disturbance, mainly for I refer it for transient type, because they are referred to severe disturbance, severe transient disturbance of this type, fault type or loss of large generator or the load here. In these situations, because for these large disturbances, it will result into large deviation, or we call it excursions, large deviation in the angle, rotor angle, power flow, magnitude of the power flow, bus voltage, and other system variables here. Thus, mainly during the transient stability, whenever you have a severe disturbance, the operating quantities, rotor angle, speed, power flow, voltage, they have a large deviation. This is to be noted here. And I take an example here, how the disturbance and what is small disturbance and what is the large disturbance here. With this example, as shown over here, we have a four bus network, and we find that bus 1, bus 2, and bus 4, they are connected to generators here, and then they have the generation capacity in per unit as mentioned. And then these buses, they are interconnected, and then we also find that in some buses, bus number 2, and then again you have bus number 3, where you have the load connected, and in the and at bus number 3 you have only load connected here, but at bus number 2 you have both generation and as well as load connected. Now, for this situation, for this case as shown here, we have the generation, and we can find here that total generation is 2 plus 2 plus 1, so that is 5 per unit here. And as well as you can find that you have a load of 5 per unit here. So the first case, if I say that this is your T0, and this is, let's say, the initial operating point, and you find here that total generation match with the total demand, and then we can say that frequency is exactly 50 hertz, and the voltage, bus voltage, is exactly 1 per unit here, right? Now, if I take a next one, so at the time t1, what you find here that, let's say there is a load disturbance, load change here, right? And as in this case, if you observe, the load at bus number 3 has changed to 3.8, and for at the bus 2, load has increased to 1.02 per unit. Now, in this case, total generation and the demand, because I consider load and demand constant now, they are not changed, right? But the generation has changed here. But again, in this case, there is a change, a decrease here 3.8, and but here there is a increase of 1.02. Now, the bus voltage, but in this case, if I say that total generation and the demand, it is same actually, right? But at the bus point here, when we say at the bus point, when we say what is the frequency, and then the bus voltage will not be exactly 1 per unit here, right? Now, for this case, as shown, we have actually from the initial operating point for the bus 3, and then for the bus 2, the changes in the load, it is just up to 5% here, right? Now, if I take another case here, now you have, let's say, another instant of time, load changes, and in this case, if I consider that from the initial point, initial operating point of 3.8 per unit, load changes to 4.25, and however, and the same way for bus number 2, load changes to 1.25. Now, in this case, from the initial operating point, these are the changes here. And then you have your generation here, right? Now, what will be the frequency here? What will be the frequency deviation And then again, it is obvious that the voltage at these buses, they will not be exactly 1 per unit. Now, if you have this form of the disturbance and it is in fact greater than 5% change from the initial point, and thus it is we can say it this one as a small disturbance, and this is we can refer them as a large disturbance. Yeah. Now, in the category of large disturbance, there can be also, let's say, a line trip here. So that means the line that connects the bus 4 and the bus 3, it disconnected suddenly. So this is then in that case, the power flow in the line is suddenly interrupted. And then this is also a form of a large magnitude change, right? That is the power flow in the network. So this is also another example of large disturbance. Then another case could be, let's say that this generator develops some fault and then suddenly this generator goes outage. Now for these cases, what we have for these scenarios, now we have to, are we able to maintain the synchronism or the stability? That is the question here. Whether it is obvious that for the case of a small disturbance, we are able to achieve the stability. That means we are able to achieve the steady state point following the magnitude of disturbance change. But for a large disturbance case, the challenge will be how we are able to achieve the stability. Because power system stability, when we say it is the ability of the power system to change from initial steady state point to a new equilibrium point following a disturbance. So following a disturbance can be up to a small amount or it can be of large amount. Yeah. So thus it will be important that to achieve the synchronism or the stability at new operating point. Yeah. Now here I have one slide. In fact, if in case you are not able to have the stability retain or achieve following the disturbance, and that is to say that if following the disturbance the system becomes unstable, and then if there is a instability, so thus there could be a situation of runaway on or the rundown. So depending upon the variable associated to lead to instability. Yeah. So here there could be a case that you have increase in the angular difference between the generator rotors here, or there could be a decrease in the bus voltage here. Now this is referred as runaway situation. That means angular difference increase between the generator rotors, and then rundown situation will be a decrease in the bus voltage here. If we take this figure as shown, so we have a 50 hertz, and following the disturbance here, if there would be some oscillation, there is some oscillation, right, in this and in the variation of the speed, and if in case we are able to restore back the 50 hertz signal, right, frequency of the signal, if we are able to restore back, then it will be referred as stability. But if in case we are not able to retain back the 50 hertz signal, right, then in following the disturbance, then it will be referred as instability situation. Yeah. Now here we have some of the real examples of instability, and in this case, as you observe that there is a bus angle suppression from Comau and Sundance. So we find here that the bus voltage of Sundance substation has a progressive increase here, right, with respect to the bus angle of Comau. And another case, this I referred it from, this is the figure shown for British Columbia and Alberta. And if I take another one, this is the case of a decrease in the bus voltage at Malin station, and you can find here that there is some oscillation you find in the bus voltage up to 23 seconds here, but what you find that beyond 23 seconds afterwards, there is a progressive drop. There is a progressive drop in the bus voltage from 550 kV to 300 kV in a time span of 6 seconds or 7 seconds. So that means in 6 or 7 seconds, you have a drop in the bus voltage from 550 kV to 300 kV here. So thus, this is from Western North America interconnected system that I have referred. And here this refers to the rotor angle instability. And this one we call it as voltage instability. And some of these figures I have referred from the lecture by P.S. Kundur. Now, because of this instability, there had been a series of blackout worldwide, and particularly if I refer to the year 2003 and 4, there had been several of them, and that's why I have listed here. And you can see that on August 14, 2003, the blackout in the northeast of US Ontario, a loss of 63,000 megawatt, and then 23rd September, that was in southern Sweden and eastern Denmark, blackout, and it led to the loss of 6,500 megawatt. And then following 5 days from this, we had the blackout in Italy, and it led to the outage of 50,000 megawatt. And then again in the Australian continent, we had a blackout on 12th of August, and then but here the loss of load was something 1,000 megawatt. Now, in this slide, we define, we are interested to know how we classify the power system stability, because we have defined the stability, but the power system stability, as I said, that it is the ability, but again, when it changes to the new operating point, there are several operating variables associated to it, and thus based on these variables, which may lead to instability, we have defined, we have the classification here. So with the quantity or the variable associated to the stability, we have the classification, and this includes the first one, rotor angle stability, frequency stability, and voltage stability. Then again, previously earlier we discussed that stability will depend upon, that means change in the new operating point will depend upon not only on the initial operating point, but also on the amount of disturbance, and thus whether the system is subjected to small disturbance or a large disturbance. Yeah. And thus, for the case of rotor angle stability, we say it as small signal stability or transient stability. And then for the case of frequency, we don't define here as per the based on the magnitude of disturbance. And then in respect to the voltage stability, we say it as a large disturbance voltage stability and a small signal disturbance here. Then again, what is the time span for the stability analysis? Because as you look into the previous slide here, we find here that rotor angle instability takes place just in, you can say that 1 second to 3, because this is 3 seconds and this is 5 seconds here. So in a span of just 1 second or 2 seconds, the rotor angular suppression takes place here. Then similarly, if you look at on this side, for the case of voltage instability, you can find that from 6 seconds to 7 seconds, in 6 to 7 seconds, there is a drop in the voltage here. And thus, it is important that what should be the time span, what should be the duration for stability analysis, that is important here. And thus, the last one, the last category that we consider for further classification of these stability types, we have it for rotor angle, it is as short term. So for the case of rotor angle stability, we say is as short term because rotor angular suppression between the bus voltage, or we can take place in a fraction of 2 seconds, 3 seconds, or 4 seconds. And thus, we are not interested in the long-term stability, because instability takes place in 2 seconds and 3 seconds only. And thus, we are interested for rotor angle stability analysis just for a small duration. However, for the case of frequency stability, we may have short-term or the long-term, because in the case of frequency stability, we mainly have to control the generator part, and we refer to the active power control. And active power control is achieved through governor operation, and governor has basically two loops in control. One is the primary control loop, another is the secondary control loop. And as such, depending upon which control loop each default in analysis, based on that, we can have it as a short-term stability analysis for frequency or the long-term. Now, in the case of frequency, short-term stability, frequency stability analysis, this time duration can be in the range of 5 seconds up to 10 seconds, 20 seconds. And however, for the case of long-term stability analysis, when we have the secondary control loop in operation, then in that case, we can have, let's say, several seconds to few minutes, 1 minute, 2 minutes, or 3 minutes as well. That could be the duration for frequency stability analysis. Similarly, if you consider the voltage stability, we can have short-term just for few seconds. That means, let's say, for 10 seconds, 20 seconds, something, or maybe for a longer term here. That means several seconds up to 1 minute here. Right. And then again, this slide I refer it from the lecture by P.S. Kundur. Now here I go further on rotor angle stability. And what is rotor angle stability? Because equilibrium criteria that we have in the chapter, it is more or less related to the rotor angle stability here. Because the P delta characteristic, that is P on the y-axis and delta on the x-axis, that is more associated to the rotor angle stability here. And what is shown here in this figure, what you find that on the x-axis we have the time duration in second, and then on the y-axis we have the rotor angle difference. So what is this rotor angle stability? It refers to the ability of synchronous machine in the interconnected system to remain in synchronism following the disturbance. That means if you are able to maintain the synchronism operation of the generators in the network, synchronism operation of the generators in the network following the disturbance, then it is a rotor angle stability. So, and it will be the ability of the generator in the system, in the interconnected system. That means you have one generator here, another generator here, another generator here, and all these generators, they are interconnected through your line here. So you have several generators in the interconnected network, and you are able to maintain or you are able to make them maintain in synchronism operation following the disturbance. So that will be the ability of defining the rotor angle stability. And thus, as shown over here, we have several generators, right? And what is shown here, it is the rotor angle difference. So let us, because normally, if you know, even for the power flow analysis, for one of the bus, we consider as a slack bus, and that is your reference bus here. And thus, we want to know what is the rotor angle difference of one bus with respect to the slack bus or the reference bus. And thus, as shown over here, generator 1 angle is considered as your reference bus, as a reference quantity, and for we want to know the angle difference of remaining generators, that is n-1 generators here. And as you can see here, these green plots, and that is the rotor angle difference between generator 10 to generator 1 with respect to generator 1, and so on. Then again, so you find here that there is a rotor angle oscillation, that means rotor angle difference oscillation of these generators. Then again, you have black curves, black plots for some other generators here. So, and again, you find here that the oscillations of these black plots, they are very much different from those of green plots here, and they can find that they are of a higher magnitude of oscillation here, right? At this moment, I will not say what is the frequency of oscillation, but I can say that what is the magnitude. So the rotor angle oscillations of those generators which are represented in the black plots, they are undergoing higher amplitude of oscillations here. Then again, you find here that one of the generator, that is generator 9, rotor angle of generator 9 with respect to generator 1, what you find here that it is of represented by blue plot. And you can see here that for this generator, it has a swing up to the maximum amplitude here, and beyond that it goes further increase here. So what you find here that in the case of generator 9, rotor angle swings to the maximum point, maximum amplitude, and then it goes on increasing further, that means deviating out with respect to the other generator here. And this is actually can be compared at generator 9 going to first swing instability, because in this case the generator goes out of synchronism on the first swing itself. So, and this is referred as first swing instability. Now, what is this frequency of instability? Well, that means the phenomena of instability. It is actually the increasing angular swing of some generator. So as shown over here, it is just for one generator. So it could be the increase in the angular swing of some generators leading to the synchronism with respect to the others here. So in fact, these generators, they were interconnected, but following the disturbance, we find that one of the generator loses the synchronism with respect to the other. That means it falls back here. So in this case, you have the rotor angle swing. Yeah. So it is not in synchronism with respect to the other generators in the interconnected system. And that is the, you can say, the phenomena of instability in the system. Now, this will depend on how well, that means how well you are able to restore the equilibrium, or you say how well you are able to maintain the equilibrium between the two torques. One is the electromagnetic torque and another is the mechanical torque for each machine in the system. Yeah. Next, I discussed the case of voltage stability, and in fact, this refers to the ability of the power system to maintain steady voltages at all buses in the system. So that means you have your interconnected system, and now it is important to maintain the steady state voltages on all these buses. Or otherwise, if you allow, so the variation in the voltages on these buses have to be within the limits here. So that means if it is the ability of the power system to maintain steady voltages at all the buses in the network following the disturbance. Yeah. So as shown over here, thus it is important that in the interconnected system, voltage have to be maintained at a steady state quantity. And as shown over here, you can refer that on the x-axis, we have the change in the power, and this is active power. And on y-axis, it is the voltage variation. And remember one thing that though it is agreed that the variation in the voltage is dependent upon the reactive power. Because if I say that you have reactive power demand, and this is perfectly matched with reactive power generation. So that means if I say that reactive power generation and the demand, reactive power demand is perfectly matched, then voltage remains at a steady state condition. But what is referred here, because normally we know that we have mostly the inductive load, and these inductive loads they never operate with a unity power factor, and thus it is not to be directly related. That means we cannot say have the relationship that means change in the reactive power. So because as we find here that if we change the active power demand here, because with the change in the active power demand, voltage is changing.